HPL-DPU and X-ScaleAI-DPU packages. And it will be presented by Dr. Donglai, who is a chief engineer at X-Scale Solutions and leads the company's R&D team. He has been the principal investigator for several current and past DOE SBIR grants. His current work focuses on developing scalable, efficient communication libraries and performance analysis tools for distributed and parallel HPC and deep learning applications on HPC systems. He has more than 20 years of industry experience in engineering management and development of computer systems, VLSI, IoT, and interconnection networks while working at Intel, Cray, SGI, and startups. He holds more than 10 US granted patents and has published more than 40 technical papers or book chapters. He's a member of the steering committee of Software Checkpoint Restart Standard and as a holder of a PhD degree in computer science from the Ohio State University. So welcome, Donglai.
Thank you for the kind. Yeah. Thank you for the kind introduction. And this is based. We have a demo on Monday, so this provides some more performance result on top of that. And so since we have much a small cloud, so ask me any questions at any point if you have one. Okay. So this one, I will just give you, this talk, I will just give a brief overview of our company because we're a startup. And then I will discuss 3 different products currently we offer. And we actually have more products, but I'm only going to focus on these 3. And the common thread for these 3 is they're all using the Bluefield DPU series for offloading, especially for non-blocking communication. Okay, so the X-Scale Solutions is founded, actually started operation in 2018, so about 5 years plus existence. And we basically provide end-to-end innovative and efficient communication solutions. And we also provide commercial support as well as training and other services for our product. And the commercial support, I'm going to emphasize just a few. Okay, of course, we guarantee our service time with different level of service. Means you will get our response in a predefined time. And we specifically doing application level as well as platform level optimizations. Okay, we're tuning our library for whatever you ordered, of course, with the existing system we have. And we also give you free updates if it's during our service license time. If we have updated, by the way, we do update quite frequently. You will get that update for free. Okay. So, and we, as a company, I forgot to mention, this company is funded by Dr. Panda, okay? And that was, most of our work is built on top of MVAPICH, open source. And there is a closed source MVAPICH version, which we don't use, okay? We only build on top of the open source part of it. And we're extending that for new kind of hardware features and make sure we can take advantage of that. And so we, as a company, we're winner of multiple Department of Energy, US Department of Energy, and so-called SPUR grants. And currently we actually have 2 second phase already in progress currently. And we actually, the product itself, we focus on communications in distributed and parallel system for both high performance computing as well as deep learning or AI related stuff, okay. And so next, I'll just go through each of the three DPU-focused enhancement to the product, to MVAPICH library. Actually, some of them focus on the deep learning stuff. Okay, so the first one, this is a major one, it's called MVAPICH2-DPU. And we have quite a few series already, and the latest release is May of this year, okay? And it's compatible with MVAPICH2 2.3.7. If you guys here remember clearly, you have a newer version, right? And that one we have not leveraged yet, okay? We're based on 2.3.7, not the 3.01. And the second thing is, with the latest release, we actually use NVIDIA's so-called GVMI-based remote access, remote RDMA framework to do the offloading, especially for non-blocking collectives. Okay, and we are using a common framework, but we implement each of the collectives with their own pattern and leverage that characteristics. And currently, for using this framework, we have completed I-auto-all, non-blocking auto-all, as well as non-blocking broadcast. Okay. And maybe let me say a few more words. For both of these two, we actually support subcommunicator. So you can have multiple subcommunicators, as well as we support multiple calls to the same communicator, allow pipelining as well as overlapping, because it is non-blocking. Okay, there's many opportunities to explore for that to show the benefit. Okay, so this one is, so the key thing here is we show the capability we are able to explore for overlapping, because the application side indicated that the communication is not dependent, not data dependent on the communication. You allow this overlapping because it's non-blocking, right? So based on that, we are able to achieve, this is using micro benchmark level of OMB, the OSU micro benchmark OMB, to show the ability we can actually achieve. This is for one of that pattern, basically is I-auto-all, okay? We are able to achieve close to 100%. Depends on the size of your system, all that type of thing. Okay. And but even for the smaller size, we're quite high, in the high 90s for this communication pattern. And by the way, we have done this for other communication pattern as well. And we have seen the achievable changes, but mostly it's more than 50, 60%. Okay. So this is still using a micro benchmark, the OMB micro benchmark, to show the performance with or without offloading to the DPU. And the red bar is showing the same benchmark running, okay? And we're showing this on different message sizes. And here, because I'm going to show more details, I'm breaking it down to small messages, medium-sized messages, then large-sized messages. Okay. And for this slides, I only show, this only contains the small messages. By small, I mean here we're showing 4K to 32 kilobytes. Okay. And just a moment. Why is this frozen? Okay. Then this, okay, now I can see that now it's moving. Okay, yeah, that's fine. Yeah. Okay, and on the left, you can see this is 32 nodes, 32 nodes of the host. And each of the nodes, we're using 16 ppms. Okay, 16 ppm, basically how many threads, how many cores we're using per node. Okay, on the right, we're showing the maximum full subscription for this system. It's 32 nodes, 32 ppm. As you can see, the achieved overlapping is similar, but the full subscription we seem to show high because we have a separate DPU unit, okay, to do the overlapping. And this one is a medium size. Sorry. Oh, this is a large size. Okay, this is a medium size. It has some delay on the to my complete. So this is a medium size from 64K to half meg. Okay, you can see the achieved benefits coming lower, but still significant. Okay, to about 50 up and down, 50%. The other one is up to 80%. Okay, and a similar thing you can see. At this one, it's more or less comparable on both sides. Okay. Now, once you go to, okay, this is the large message sizes. Okay, and more or less you can see it's sustainable. It's up and down around between 50% to 60% or something slightly above that. So this is even from 1 megabyte to 16 megabytes. We have actually tested even larger ones. One we have that system available. Okay. So this is quite consistent from micro benchmark perspective. The lowest one allow us to do the overlapping and achieve performance benefit. Okay, this is I auto all. Oh, sorry. This is medium set. This is large set. Yeah, this is. Okay. And this one, why do I mess up the order? Okay. Then let me talk about this first. And this one is for non-blocking, still at the micro benchmark level, talking about non-blocking bcast, broadcast. Okay. And again, we're showing, this is showing at 16 nodes. It depends on, at the test availability of the system. So this is on 16 nodes, and it's half subscription and full subscription per node. And as you can see, again, this is performance benefit is between about 50% to 60%. Okay, this is actually for large messages, from 1 megabytes to 16 megabytes. And we also see similar things to even higher ones. Okay, next, we are going to see at the application level, so-called computational, which means we have the real computation compared to which contains some communication. And this is P3D FFT, one of the applications we use. It's actually a computation kernel. And this result shown from the application perspective, the latest library are able to show that the performance margin, and it's here for the data we take is showing up to 24%. And we have data to show this margin is quite sustainable for other cases, if it's reasonable cases. Means you're not doing too much of a skewing or imbalance in your computation or that type of thing. Okay. And so this one is for different input sizes, because the different input sizes, the computation and communication ratio sometimes changes a little bit based on your application itself. And this one we can see, this is for different input sizes. This is for the same compute grid, means 32 nodes and 32 ppm. Okay, and this is showing for different problem sizes. It's quite sustainable and consistent with the performance gain. So there we remember, there we see for small messages up to 80%, okay, which is using micro benchmark. This is showing application level. And for the middle ones is about 50% or up to 60%. And based on the computation and communication ratio, that will give us some indication how much we actually are able to explore this. Okay. And next, we're going to talk the second package. This one is actually HPL benchmark. This HPL benchmark is actually used for ranking all the top 500 systems in the world for supercomputers. Okay. And we basically redesigned the code. We do some redesign for this code based on the latest release of the benchmark, standard benchmark, which is HPL version 2.3. And we designed it to use our latest library, okay, so that it can do some more intelligent overlapping, okay. And also doing some parameter adjustment optimization on this kind of thing. And basically this benchmark, because we are using this as a benchmark to show the effectiveness of the DPU offloading. So we modify this code to have two different modes. One is without using DPU, the other one is with using DPU, okay? And here is the result. And I'm only showing the result compare of our two modes. And by the way, we have done even some tests with this host-only mode, which is the red here, compared to other libraries available to the system we're doing testing. And for each of the cases, the red one is better, performance-wise is then better than all the other, like Intel library, HPCX library, all that, in host-only mode, because those one only support host mode. The red one performs the best, okay? So that's one of the improvement. One after we restructuring is actually benefit the host-only mode as well. And then with the DPU enabled, which is the red bar, okay? Now, one thing you may notice, this is going up. And the thing is, we're measuring it differently. This is not measuring the time. This is measuring the flops per second. So higher is better. Okay, so another thing you may notice, as the input size is increasing, this is true for both different compute grid. The performance is increasing. And our margin is reducing. Improved margin is reducing. One reason for this is the HPL itself is actually actively avoiding communication. Okay, some people actually get quite frustrated because a lot of things you do at the communication part does not impact the overall performance that much, okay? Now, what we are trying to say is, you look at here. So as you achieve so-called HPL used for ranking the highest performance, it's a peak capability of the system, okay? So what that means is you push everything possible to get the last, how do we say, last piece of the benefit to do the computation. But for most of the system, even for the larger system, when in the real usage, sometimes you don't allow to use the entire system to do your own computation, simulations or whatever. So on a daily basis, not pushing the entire to reach the peak is that the only thing you care about. It's more typically you get some portion of the system, okay, and you try to run that with a fast turnaround time. So the daily operation efficiency matters as well. And for those ones, you can see, as you have not pushed the very limit, then the efficiency for the communication here is quite, benefit is quite noticeable, okay? Say it, about 10% or around that 10%, you will see the benefit. And in other words, this allow you, not fully system, to get almost the best performance as you can achieve with whatever resource you have been allocated. Oh, sorry. Okay, now I'm going to touch on the last piece of our product. Okay, so this one is actually purposely built for deep learning, the AI platform. And we're offloading some of the functionality. And for this particular package, it works for PyTorch, okay? We actually offloading some of the functionality to the DPU to help to improve the overall performance of the platform. And this package itself is compatible and built on top of PyTorch 1.12.0. That's what is available at the time. It's May of this year, okay, the most stable system platform at that time, because they also keep updating. And this is based on PyTorch as well as Harvard. Harvard version is 0.25.0. And again, we're building for communication we are leveraging on the 2.3.7, okay, compatible to that. And so we are, the main innovation is we're offloading some of the computation steps of the training as well as some IO related stuff. This is one of the, I think I'm going to show two different results. Yeah, this is one of the deep learning sort of a benchmark. It's for this particular one, the right is showing the hardware system we're using, which actually is the same as what we used before, okay? And I'm only going to show this, explain this result. So this, the task is doing the deep learning training model is ResNet 20 version 1. Okay, that's one of the popular ones, and is used one of the standard data set is Cypher 10. Okay, and here the task is done up to 32 nodes. That's the largest system we can get on our test bench. Test bed. And we're scaling it from 1 to all the way, power of 2 to 32. So we're trying to see the scaling part and see how the performance margin performance benefit is behaving. As you can see, so this basically is a strong scaling case. And what we're trying to see is whether whatever we're offloading, the benefit is sustainable, is diminishing, increasing. And as you can see, the blue line show basically improvement, and the scale percentage is showing on the right. And as you can see, this actually, as you scale the system up with the same given problem sizes, same problem size, and the benefit actually is quite sustainable. It's turning up a little bit, but we have seen it's stabilized. Okay. So this one is above, around 15%. Okay, actually in our live demo 2 days back, we always see 17% for all the tests we've done. Okay. Okay. And this is another example of deep learning. So this is training model for that model is a ShuffleNet, and used tiny ImageNet data set, which is another popular data set for deep learning. And a similar thing, we're doing the test for, as we scale up the number of nodes, and each node scale 32, up to 32 ppm, whatever is best for the application we are using. And as you can see here is, again, as you scale down, scale up the number of nodes, basically the system size is computed with the same problem size, and we're seeing the performance benefit margin is also stable. Here is more or less 12%. So for different applications, deep learning applications for training, we can see this platform, this package is able to see more than 10% performance benefit. Okay, so that's the package, and whatever we have done to this use offloading is able to achieve. Okay, now next, this is in addition to the offloading itself, it's specifically doing the offloading for checkpointing. Okay. I should say the previous we focused on the communication offloading. This is focused on the checkpoint offloading. Okay. And because deep learning, especially for training, we have seen the need for checkpointing. It has been done as a default in your framework. And like a PyTorch also has the torch save, I think, that one. And for end user, you may not notice that, but it's called because, especially when you have long runs with a small cluster or something, that it becomes even more prominent. So this is illustration of what we have done. And by default, it's on the right. No, on the left, sorry. On the left side, it shows by default. On the right is something we have done, change the scale. So on the left, you can see by default is every core, whatever. Here we only illustrate 4 cores. So 4 ranks, you do your distributed training, and once you reach the checkpoint, everyone stop. So one of basically the rank 0 will save the checkpoint, your model. Okay, then your training will resume after the checkpoint is completed. And with this, whatever we have done, we say, okay, we think most of the time it gets wasted. So with a non-blocking one, which we have, that we allow this one is actually what we did is we are doing something on the background. Okay, we're non-blocking on the background. So we are using multiple hierarchy of the storage. We're using node local storage to take a snapshot of your checkpoint. And then we'll back up that the image or whatever checkpoint files to the shared file system later in a synchronous manner. Okay. And this is showing the benefit when you achieve that. As you can see, and we can start the next iteration or whatever that iteration is right after you checked it on your fastest storage layer. And as far as the package or the application is concerned, you don't see the difference. So most of the work is done by the backend. Okay, to make sure your checkpoint is stored properly. And here is the performance difference benefit. Okay, and for this one we actually check I think we did this checkpoint under this is number of nodes. Okay, we tested up to 8 nodes, and we did node checkpoint. Okay, that's the red one. That's the best performance you can hope for. Okay, then we checkpoint. We put 4 checkpoints per iteration if that iteration is long. Okay, and this so-called root is the default. Okay, then the offloaded version is our framework version, the purple one. Okay, so the yellow one is the highest. So that's where we're comparing. So in other words, the red one is the upper limit from performance perspective because you are not doing any checkpointing. You have no overhead at all. Okay, the yellow one is whatever the default is. Okay, so that's what we're competing against. Then the green one is whatever we're doing offloading, as well as the purple one. Purple one, we are doing the same number of checkpoints. You can see the performance difference. Okay, and the green one is we actually double into 10 times instead of 4 times, increase the number of checkpoints. Okay, that means you have less of a work wasted in case there is a failure. And then more normally people think that you will increase your overhead. We did, but even with that increase, we actually see still noticeable performance benefit. Okay, so you get a higher insurance on work preserved. Okay, and so here is the conclusion. So we provided brief overview of the company, and we also overviewed most of the product we provided, especially those products based on DPU offloading. And we have shown that these products provide high performance as well as with scalability. Okay, and we are looking to extend our work to not only CPU, DPU system, but also with a mix of GPU inside. Okay, and we are looking at all these 3, how to balance them out. And we are also looking to, we are work with a few third-party customers as well as collaborators. Okay, and we are looking for more. Thank you.
We don't have much time left, but we can take a quick question if there is any.
Let's assume that we run two different applications on the same compute node, and one is for HPC application and the other is AI application. And we want to apply the DPU offload you suggested for HPC and AI together on the DPU. Is it possible, or do we consider some issues to apply those kind of idea?
Okay, that's actually quite challenging. Normally, when we do parallel computing, we reserve the system. Okay, we don't mix them. Okay. Yeah, you are looking for potentially interactions or competing, right? And be honest with you, we have not tested that. Okay, but from a design perspective, we are keeping all this separate. Okay, so there is no damaging effect except potentially performance interference when we reserve shared resource. Yes, I expect that, but we did not investigate that effect because nobody actually has asked that for such a mix. Okay. Yeah, go ahead. Can you repeat that? Sorry.
According to your presentation, you mainly compare the CPU-DPU system against the CPU-only system.
Yes.
Is there a reason why you don't use the GPU-based system?
Yeah, that's actually a very good question.
One of the reasons why I'm asking this question is that, I'm sorry, but one of the reasons why I ask this question is that in a GPU-based system, the GPU takes up the most of the computation part. So your CPU or one or two of the cores within the CPU can take, for example, the checkpoint desktops.
Yes.
So in that configuration, the benefit of a DPU may vary. I mean, it's going to be quite different.
That's a good point. Actually, from pure performance perspective, okay, depends on what kind of things you have. If you noticed, for the very small messages, we don't see benefit for offloading to DPU because of overhead. So we actually dynamically detect at what point it's beneficial to do the offloading. Okay, we have built-in intelligence for that. Okay, and in general case, one thing, we did not investigate the GPU, CPU, and DPU mixed system is because our test environment does not support that yet. Okay, so we can do design, but we cannot test. Okay, but we're starting to have that request in place. So that's one of the directions we are going to extend. We do see that it's going to be more popular. Okay, and the other thing we did notice is DPU, especially with upcoming ones, DPU and IPU, means Intel's one, they actually try to separate the functionality between CPU and DPU. DPU has other considerations, not only for performance, for security reasons, for service stability, all that, even for IOs. We try to move into the DPU, okay? So in that case, it still makes sense to investigate this mix, not only from a performance perspective, but for the trend for the industry, as well as for national labs, because security is one of the main concerns there as well. But to answer your question, no, we did not reach that point yet.
Yeah, so let's take a short break. So as some of you have, again, still flights and all, what I was thinking is instead of take a 10 minutes break, have coffee, and then 3:50 we'll start, so that it'll allow everybody to have enough time to leave. Yeah, 3:50. No, 3:50, 50. Yeah.